All right, everybody. Very good to see you all here this afternoon. How's everybody doing today? Excellent. Doing excellent. This is what I like to hear. Good. How's everybody else doing? I'm generally seeing thumbs up. Okay, very good. Oh, some thumbs up back there. Thumbs down? Double thumb. Why double thumbs down? Bit hungover. Okay, well, do your best today then, okay? So, great. Well, that's right, kinematics. So the lecture today, we're really following directly on from the kinematics that we were doing on Monday. So on Monday, we introduced displacement and velocity, and we just saw a bit about acceleration. And the real theme for today is all about connecting displacement and acceleration. So it's really asking the question, what's our displacement going to be if we're accelerating? And just to emphasize why this is such an important question, that understanding this situation, it's really essential in a couple of weeks when we're going to be thinking about energy. It's really essential to understand this kind of situation here in order to understand energy. And whichever subject you're studying, energy is such a crucial central concept. So that's why it's such an important thing for everybody to think about, okay? Now, usually we have a bit of a kind of plan for today, but we're really today picking right up from where we left yesterday, okay? So let's start with a quick recap of where we got up to not yesterday, on Monday. Thinking about velocity and acceleration. So we were thinking about this situation here where we had an apple and it was falling off a tree and it accelerates towards the ground and then it hits the ground. And the reason this is a good one to think about is because, of course, in that story you had Isaac Newton and he was sitting under the apple tree, and, you know, the story goes the apple hits him on the head, and that's what makes him think of gravity. And I think there's some level of doubt at exactly how historically accurate that story is, but I think it's still a good, it still sort of makes the point, doesn't it? So what we had is that acceleration, it's how much our velocity has changed, divided by how long it took for that velocity to change. And then we can do a bit of algebra and rearrange it and get what our velocity is, okay? So let's start with a quick kind of warm-up practice question. Let's think about how fast this apple is going to be hitting the ground, okay? So it's going to fall off the tree, and we know that it takes 0.0 seconds to hit the ground. So maybe we're watching the apple, maybe we've got a stopwatch there and we time, and it takes 0.6 seconds to hit the ground. So let's have a go at working out how fast the apple is going to hit the ground. All right, everybody, let's take a look at the results. Let's see what we get here for how fast the apple hits the ground. Oh, okay, so nobody's going for B, but then we've got pretty evenly split between A, C, and D. Okay, so very well done, everybody who gave this question a go. So when it comes to crunching the numbers, figuring out what we've got here, so we know that acceleration due to gravity, it's 9.81 meters per second per second. That means if the apple had been falling for a whole second, it would be falling at 9.81 meters per second. But it wasn't falling for a whole second, it was only falling for 0.6 of a second. So it's going to be falling for 0.6 times 9.81 meters per second. So the question is now, which of these is the correct option? And I'm seeing quite a lot of people going for A. In fact, it's evenly split between A and C. So does anybody have any thoughts? What's the difference between A and C? Which one might we want to be going for? Any thoughts? Got some ideas over here?
I'm guessing like C rounded up.
Yeah, so do you want to be going for A or C, do you reckon? You're going for A because it's not rounded? Yeah. Okay, does anybody want to go for the C camp, for the C option? Yeah, you over there? Yes, Sam?
Because it's the the same as what's in the question, so they have significant figures. There's 0.6 is one.
Absolutely right. Absolutely right. Very good. Very good. Did everybody hear that? That's a really good point. So remember significant digits. So how many significant digits do we have in the time? We only have 2 significant digits. So we only get 2 significant digits in our result. So even though the number that comes off your calculator is 5.886, the correct answer is option C, 5.9. Okay, so very well done, everybody who gave that one a go, especially if you got option C, because you have to watch out for the significant digits there. And very good for the explanations there. Okay. Let's try another kind of recap warm-up question. Let's this time, so that was a bit of a kind of calculating question, and you know how much I like to relate the calculations to what's going on with the diagram. So let's try a bit more of a kind of diagram question over here. So in this question, we've got a graph of the acceleration of our apple when it's falling against time. So the question is, what does this area, as we say, under the graph correspond to? And remember, you know how much I like units, so think about what the units of this area on the graph are going to correspond to. Okay, let's take a look at the responses. Let's see what everybody got here. Okay, so it looks like most people are going for C. Now, if you're not sure about this one, they are a bit tricky, but you don't have to guess because we can always look at the units. So let's look at what the units of the horizontal axis are. That's seconds. And then the vertical axis, that's meters per second squared. So when you have meters per second squared times seconds, the units of that shaded bit of the graph, it's going to be meters per second. And those are the units of velocity. So the area of that shaded graph, it corresponds to velocity. So very well done, everybody who got that one, that it's velocity. If you're not quite sure about that, it can be a bit kind of counterintuitive thinking about an area and it's not, you know, an actual area, but it's something that gets easier with practice. So we'll have a few more of these questions and I'm sure you guys will get the hang of it, okay? So very well done, everybody who gave that a go. Let's try one more quick kind of graph question because it's really important to know our way around these kinds of kinematics graphs here. Suppose we have a graph of acceleration that looks like the graph up top there in the red line there. So we've got some acceleration versus time. We've got some things going on there. Which of these 4 graphs of velocity versus time corresponds to that graph of acceleration versus time? Let's see what you guys think for this one. So remember the acceleration, it's going to be the slope of the velocity versus time graph. So think about the slope of all 4 of those graphs. Which one is going to give us that acceleration in the top there? Let's see what we have here. This is a bit of a tricky one. Let's have a look. Okay, so A and D mainly. So A and D. Okay, now it's always helpful with these to kind of tell yourself a bit of a story. Think about what might be going on here. So let's take a look at the acceleration. To start with, the acceleration is positive. So whatever it is, it's increasing its velocity. And then halfway through, the acceleration goes negative. So they're putting the brakes on. So maybe what's going on here, maybe you're in a car and you put your foot on the accelerator, you're getting faster, and then you get fast enough and you hit the brake and then you slow down. So which of those graphs corresponds to that? So the only one, it's the top one where we've got our velocity increasing and then it reaches a maximum and then we decrease. So the correct answer, option A over there. So very well done, everyone who got that, okay? If you're not sure about this, it can be counterintuitive when, you know, the graph goes through 0 and what's going on here. So remember, when we're relating velocity to acceleration, the acceleration is the slope of the graph. So it doesn't matter whether we're above or below the axis. The only thing that matters is the slope of the graph. So if we look at graph D here, the slope starts off negative and then it just keeps going negative, just keeps going negative. So we don't have that situation where the acceleration is changing like that. But it can be a bit tricky. It just gets easier with practice. So very well done, everybody who gave that one a go. Now that we've had a few kind of warm-up questions, what I'd like to do is take one slide to kind of recap everything we've seen so far and put it all together on one slide. So we've got everything we've seen so far. So we've got these three graphs here. So we've got acceleration, velocity, and displacement versus time. If we have this situation here where we've got constant acceleration, so our acceleration is constant, we know that our velocity is going to be changing constantly. In this situation, our acceleration is positive. So if our velocity started out at 0, we have positive acceleration, our velocity is going to steadily increase. So our velocity versus time, it's going to look something, we've got the shaded region, and our velocity is going to look like that green line there. So remember that our velocity, the green line, it corresponds to the area under the graph of acceleration versus time, so that shaded area. Who's done a bit of calculus before? Okay, a few people. Okay, so if you've done calculus before, then we can say that the velocity, it's the integral of acceleration with respect to time. If you haven't done calculus before, what that means exactly is that it's the area, that shaded area there. That's going to give us the velocity versus time. We can apply the same kind of idea to get from velocity versus time to displacement versus time. What makes this a bit more interesting, though, is that in this graph here, our velocity is constantly changing. So our velocity is constantly increasing. This gives us a slightly more interesting result for our displacement versus time, because the displacement, it's the area under that graph there, and that area is constantly increasing. So that green shaded area, it increases more and more because the wedge gets bigger and bigger as we go along. So what that gives us for our displacement, we actually get a kind of curved line like this, which is a bit more interesting. And figuring out what's going on with this curve here, that's really what we're going to be focusing on today, really trying to understand everything that's going on with that. It's not just like a straight line or something like that. So it's a bit more of an interesting thing to think about. Once we have a displacement versus time, whatever that displacement versus time is, we can get back up to our velocity versus time by taking the slope. If you've done a bit of calculus before, we're just taking the derivative with respect to time. That just means it's the slope of that line. So if we look at our displacement versus time, it starts off flat like this. So if you imagine a tangent there, that tangent's going to be 0. It's going to have a slope of 0. So we get a 0 velocity when we start off. And then if you look what happens as the graph moves along, it gets steeper and steeper, our velocity increases. And then we get over to this side and we've got a higher velocity. And we can apply exactly the same idea to get from our velocity versus time up to our acceleration versus time. Again, it's just the derivative of this graph, it's just the slope. And our velocity versus time, that slope is constant. So that's what gives us that constant acceleration up in the top there. That's the underlying fundamental principle with kinematics. When we're studying kinematics, it's easy to get bogged down with lots of different equations and U's and V's and all this kind of stuff. But this is the fundamental principle. Whatever your velocity versus time is, we can relate it to these other quantities by thinking about the area under the graph or by thinking about the slope. That's the kind of secret to it. And that applies whatever our velocity or our displacement or acceleration is. Okay, we can always apply these principles. Does anybody have any questions about this at this point? Anything they want to ask? Okay, so what I want to think about next is a really interesting kind of kinematic situation. And it's this exact situation which is really essential to understanding energy. So let's take a look at this situation. Let's see what's going on here. So what we've got here is a very cool picture of an F-18 on an aircraft carrier about to be fired off and about to take off. So it's a very cool, very exciting situation. And what's going on here is that the F-18 is sitting on the aircraft carrier and it's stationary. And in order to take off, get into the air, it has to reach a certain velocity. In this case, it's about 170 miles an hour. So if it gets to the end of the deck and it's going slower than 170 miles an hour, it's going down into the sea. So it has to reach this velocity. What's the constraint here? The reason this is an interesting problem is that our constraint is the distance. It's how far on the deck we have to reach this speed. So in the case of an aircraft carrier, the deck, it's 300 feet. Now, it's an American aircraft carrier, so they measure things in feet. Obviously, we can convert to SI units as we like. So this is an interesting question, because if we say, well, how fast do we have to accelerate? We can't directly apply any of the equations that we've seen so far. So we do have a distance, and we do have a speed, but we can't use those to work out time because that speed, it's not constant. It starts off at 0 and it only reaches this speed right at the end of the deck just before it takes off. So if we want to know what our acceleration is, we can't directly calculate it from that equation that we've seen so far because we don't know how long it's going to take. We don't know what our delta t is. Does anyone have any thoughts about how we could go about starting on a problem like this? Any ideas? How could we go? Yeah. Okay, very good. So the suggestion that there was convert feet to meters. Great place to start. Okay, get things into SI units. Any other thoughts? Okay, so we're going to get to that. So that was using the Suvat equations. Okay, so we are going to get to that. But what I'd like to do before we get to that is to kind of understand where they're coming from. So what was it? Yeah? Yeah, absolutely. Absolutely. No, I think that's exactly right. So did everybody hear that? I think the key thing I want to emphasize there is we can draw a graph of this situation. So maybe we don't know what the equations are going to be going on. But remember, I'm almost always saying, draw a diagram of the situation, draw a graph. Whatever kind of problem you're solving in physics, a great place to start is always by drawing a diagram, by drawing a graph. So even if we don't right now know how to figure out what the acceleration is or what the time is, we do know how to draw a graph of our velocity versus time. And drawing that graph is actually essential to unlocking this whole situation. So let's try this question here. We've got 4 potential options here. Which one of these 4 graphs corresponds to the situation that we saw there, where we're starting from rest and we're accelerating up to some velocity? Which one of these 4 graphs is it? So remember, this is a graph of velocity versus time, and we're starting from rest and we're assuming constant acceleration. So have a think about which of these graphs corresponds to that situation. Okay, let's take a look at the responses here. Let's see what everybody thinks for these graphs here. Okay, so mainly it looks like B is the winner there. Some people going for D, some people going for those other ones. What have we got here? Now, I can see why people might kind of be drawn to D, because when we think about things constantly accelerating, I think it does kind of, at some level, kind of look like what we might expect, right? So it starts at 0, and as we move along, it kind of gets faster and faster, and then it reaches some maximum there. So I can see why you might be going for option D. But remember, we're assuming constant acceleration here. And this is a graph of velocity versus time. And the slope of that velocity versus time is our acceleration, which is constant. So what we're really thinking about here is which of these graphs increases but has a constant slope. And the only one that does that is option B. So very well done to everybody who got option B, because that's the correct response there. So this is our graph of our velocity versus time. So very well done if you got that, because this is a really important graph for understanding what's going on here. Now that we've got our graph of velocity versus time, how is that going to help us relate our acceleration to this distance that we're trying to figure out? Any ideas? Did you have a?
The area is going to be the gradient, and not the area, so the acceleration is going to be gradient with that, and then you can calculate the displacement with the area under that, and then you can just rearrange it and mix and match.
Absolutely right. Did everybody hear that? It was a really good explanation. So the displacement that we're trying to relate to, it corresponds to the area under the graph. So remember, whatever our graph of velocity versus time is, our displacement is always going to be the area under that graph. And this is how we're going to relate our final velocity to our displacement, to that 300 feet that we're trying to do here. So we've got that option B, that's the correct shape for our velocity versus time graph. So let's think about what the area of that under that graph is. So I've got the same graph here, velocity versus time. And as we can see, it starts from 0 and it increases with a constant acceleration. And I've put a couple of labels on it to help you guys. So we've got our time delta t. This is how long it takes to shoot the F-18 off the deck. And then over here, this delta v, that's what our change in velocity is. So it's starting from 0 and it's got to reach that 170 miles per hour before we get to the end of the deck. And then we know that that shaded area there is our displacement, delta s. So you guys need to do a bit of algebra, a bit of geometry, figure out how to relate that delta s to the delta v and the delta t there. So I'll get the question going. Let's see what you guys think about this one. Okay, let's see what we get here for this one. Let's see what everybody thinks. So remember, we're trying to figure out what the area under that curve is there. I mean, I say curve, it's a line, but I'm using those terms interchangeably. Let's see what we get here. Okay, so people mainly go in for C. Now, I can kind of imagine why some people might be going for A, because it does kind of look like a formula that maybe you've seen before. We're actually going to get to something like that. But if we look at what's going on with this situation here, we're calculating the area of a triangle, and the base of our triangle, it's delta t, and the height of our triangle, it's delta v. And of course, the area of a triangle, it's a half the base times the height there. So the correct answer is option C. So very well done to everybody who got that one. This is a super handy equation because it allows us to unlock this whole situation that we're thinking about, because we know what our displacement has to be. It has to be that 300 feet. It has to be that length of the deck there. And we know what our delta V is. It has to be 170 miles per hour. Otherwise, we're not going to take off. We're going to end up in the ocean. So we can use this equation here to work out how much time we have to get launched down that deck and take off. Let's try the calculation here. So I've converted the numbers into SI units there. So very good suggestion we had there. Always useful to convert the units to SI. So I've done the conversion. We know that the velocity, it's 76 meters per second, and the length of the deck, 91.4 meters. Now we can use all of these things that we have now and this equation to calculate how much time we have to fire our fighter jet down the deck. An interesting thing to think about this equation is what it's telling us is if we start from a velocity of 0 and then we accelerate up to our final velocity delta v, we're going to cover the same distance as if we'd been traveling that distance at that average velocity for the whole time. That's what that half delta v is telling us. Just an interesting way to think about the equation there. All right, let's see what everybody gets for this one. How much time do we have to launch our F-18 off this carrier? Okay, so most people going for D. And when you put the numbers in and you do the rearranging and you solve for what our delta t is, that's what you get. So we get 2.41 seconds there. So very well done, everybody who gave this one a go. If you didn't get the 2.41, don't worry too much about it. Maybe we can check the math, check the algebra a bit in the workshop. It's just something that gets a bit easier with practice. So very well done, everybody who gave that one a go. What I'd like to think about with this question is previously we were thinking about, okay, we know what our displacement is, and we know what our final velocity is, and we know what our time is, or those are the variables that we're considering. But sometimes we don't know directly what our final velocity is going to be. Instead, we might know what our acceleration is. So we know that our final velocity, our delta v, that's equal to our acceleration times however long we've been accelerating. So that's where we get that delta v is equal to a times delta t. And what we can do is we can substitute that into the equation we just figured out, and we can get a very useful relationship between our acceleration and our displacement. So it's a very useful relationship because it tells us what our displacement is only depending on our acceleration, not on what our final velocity is. So let's give this question a go. Let's see which of these relationships is the correct one. So if you're not sure, we're just doing a bit of algebra here. So if we start from the first one, we've got delta v and delta t, and all we're doing is we're substituting that delta v is equal to a times delta t into that first equation. So just a bit of algebra, just a bit of a substitution, see what we get for that one. Okay, let's see what we get for this one. Which of these is the correct relationship? Okay, so it looks like most people are going for option A. So remember, we start with delta s is equal to a half delta v times delta t, and we know that our delta v is equal to a times delta t. So it's a case of substituting that relationship into the first equation and seeing what we get. So we have delta t times delta t, that gives us delta t squared. So the correct relationship, it's a half a delta t squared. So very well done to everybody who gave that one a go, okay? That's really good work there. This is a really important relationship, a really useful result to have, because what it tells us is if we know what our acceleration is and we know how long we've been accelerating, what we can now do is work out what our displacement is. This is an essential kind of thing to think about if we're considering maybe things falling under gravity and we know what the acceleration due to gravity is and we want to work out how far something's fallen. But moreover, this is actually an essential relationship when we come to be thinking about different forms of energy. So it's a really important result. So very well done to everybody who figured this one out. The last situation that I'd like to think about for today, it's really extending this situation about a carrier launch here. So let's take another look at the F-18, see if we can make this a bit more interesting. So we got our F-18 again, and it still needs to reach 170 miles per hour in order to take off. And we still have the same length of deck. We still have a 300-foot deck. What makes this situation a bit more interesting is, in reality, what the aircraft carrier does is it's steaming along, and they give the jet a bit of what we say initial velocity. So they're sailing the aircraft carrier into the wind. So the F-18, it's not starting from from standstill, it's already got a bit of velocity relative to the wind. So we say it's got some initial velocity, which is going to be, say, the velocity of the aircraft carrier. Now, this makes the whole situation a bit more interesting, and we very often see situations like this when we're thinking about kinematics situations. So the question is, now that we have some initial velocity, what's our acceleration going to be, and how's that going to affect our time? Does anybody have any thoughts about how we can get started tackling this situation? Any thoughts? Don't know. Exactly. So we don't have the time. This is a good point. We don't have the time, so we can't work out the acceleration. Yeah, back there. Okay, so we are going to get to that, but how would we think about kind of getting there? How can we always, yeah? Okay, that's going to help us. So there are kind of pieces of equations that we're going to get to. But remember, if you're not sure how to start solving an equation, maybe you're working through a problem in the textbook, maybe it's a question in the exam. A great place to start, remember, it's always drawing a diagram of the situation. That's always a great place to start. It's always going to help us figure out what's going on. And then we don't have to rely on trying to memorize equations. If we start by drawing a diagram, that's really going to help us. So let's think about this situation. We're still assuming constant acceleration, but instead of starting from a velocity of 0, we now have some initial velocity. Let's take a look at these 4 options here. Which of these 4 velocity versus time diagrams corresponds to starting out with some initial velocity and then accelerating constantly until we reach some final velocity? Which one of these 4 is going to be the graph of that situation? If you're not sure, remember, it's the same situation as we saw with this question before, but instead of starting from a velocity of 0, we're starting from a velocity of something. So look for the graph which is the same as before, but just shifted up by a bit. Okay, let's take a look at the responses. Let's see what we get for this one. Okay, looks like most people going for option D. See, some people going for A and B. Now again, I can kind of see why, same kind of deal as with the question before. If you're looking for something kind of accelerating, I can see why you might think that maybe A and B, they look like something accelerating, right? But remember, this is a graph of velocity versus time. And it's our velocity which is increasing constantly. Now, these all are starting from some initial velocity, but the only one which increases constantly is option D here. So correct option is option D. So very well done to everybody who got this one. This is our graph of velocity versus time for this situation. And this is what we can use to relate those initial and final velocities to our displacement. And we can do it exactly the same way as before. It's exactly the same principle that our displacement is the area under the graph. The only difference is that this time the area is a bit more interesting. Let's take a look at this situation here. So this is the graph that you guys correctly picked out. So velocity versus time. That's the exact graph that you guys just picked out. I've just put some labels on it to help everybody out a bit. So remember, we're thinking about a time of t here. This is how long it takes to launch the fighter jet. And the only difference from last time is that instead of a velocity of 0 to start with, our initial velocity, we're calling this u. So we're not starting from standstill. And then as we're fired along the deck, we increase all the way by an amount at. So that's our acceleration multiplied by how long we were accelerating for. And exactly as before, what we're looking for is that area, because that area under the graph, that whole area, that's going to be our displacement. So it's just geometry as before, but it's just a bit more interesting because there's a few more pieces to the puzzle. Okay, let's take a look at the results here. Let's see what everybody gets for this area. What do we get here? Okay, oh, spoiler warning. Okay, well, never mind. Okay, so it looks like most people are going for A, and as you can see, it's given the game away a bit here. That's the correct result here. Now, if you're not too sure about it, let's take a look at the graph here, okay? So let's start just with the rectangle here. So the base of that rectangle, it's T, and the height of the rectangle, it's U. So the area of that rectangle is UT. So that's where we get the UT part from. And then we just need to think about the area of the triangle. And that's exactly the same as the area of the triangle we saw before when our initial velocity was 0. So the base is T, the height is AT. So the area of the triangle, half base times height, is a half AT squared. So we get these two different parts, UT plus a half AT squared. So very well done, everybody who figured that one out. That's a really great result, a really important result in kinematics. The thing I want to emphasize with this is please don't try and memorize any equations. Whenever we're thinking about something going on, I'd really suggest start by drawing a sketch of the situation and think about what's all the different pieces going on there. The last slide that I'd like to finish on today is really a kind of recap summary slide of everything that we've seen this week. Just to bring everything that we've seen this week together onto one slide and see how it all fits together. So let's take a look. So we started on Monday by thinking about situations where we have constant velocity. That means our acceleration is 0. So if we have a graph of displacement versus time, our velocity is just the slope of that. And if our acceleration is 0, we can relate our displacement to our time. It's just s is equal to vt. If that's our displacement versus time, so our velocity is constant, that's what our velocity versus time looks like. Now, what does it mean if our velocity is constant? That means our acceleration is 0. So our graph of acceleration versus time is just 0 all the way. Now remember, we can only use that equation there, s equals vt, when our acceleration is 0. So this is the situation we have for a constant velocity, constant v over there. And that's really everything that we were looking at on Monday in 3 graphs there. Then the other main situation that we might see that we're really focusing on today is the situation where we have constant acceleration, constant a. So maybe things falling under gravity, maybe a car accelerating, maybe a fighter jet being launched. These are all situations where we might have constant acceleration. So our acceleration versus time is constant. So it's not 0, but it's not changing. And then what that gives us is a velocity which is constantly changing. So our velocity versus time looks something like this. And I've written out the equation there, but it's just the equation of a line. So we start with some velocity u, and then our velocity changes by an amount at. So it changes by what our acceleration is, multiplied by how long we've been accelerating for. It just gives us the equation of a line. And then remember, we just worked out that that area there under the graph, that's going to give us our displacement versus time. And that's what it looks like. And we've just worked out that that displacement versus time, so it's ut plus a half at squared. Now, please don't try and memorize any of these equations, okay? Always try and understand where they come from. You know, with this ut plus half at squared, they come from those different pieces of the graph. And whatever situation we're thinking about, if we have maybe some displacement or some velocity, we can always get the corresponding result by thinking about the slope of this. So if we have the displacement, we can think what the slope is. That's going to give us the velocity. If you've done some calculus, it's the derivative with respect to time. That's just what we mean by the slope. And then if we have maybe the acceleration and we want to get the velocity, or we have the velocity and we want to get the displacement, it's just the area under the graph, or in calculus terms, the integral. So we can go from the area to the velocity to the displacement by thinking about the area. Maybe if you've done a bit of calculus, you might recognize, that u plus at and the ut plus half at squared. We just have the derivative with respect to time going on there. That's the relationship between the two. And these are really the two main situations that we need when we're thinking about kinematics situations. So just a couple of points to wrap things up. So first of all, these are two different situations, remember. So if we have something that's constantly accelerating, we can't use anything from this side to figure out, for example, how far we've gone. And just the last point that I really like to reiterate, please don't try and memorize any of these pieces of the puzzle. We're going to have lots of examples in the workshops where we're going to be getting familiar with them, and you're really going to get familiar, get comfortable with these equations. You're not going to need to memorize anything. So I think that's a great place to wrap things up for today and for this week on kinematics. Just a reminder, we've got the workshops tomorrow. We've got a really good challenge question in the workshop tomorrow. It's one of my favorites, so I'd really encourage everybody to give that one a go, okay? So hope everybody has a really good afternoon, and I'll see you all on Friday. So I'll see you then.